All right, welcome to section 3.2 where we talk about independent and mutually exclusive events. Starting with independent events, we know two events, A and B, are independent if the knowledge that one occurred does not affect the chance that the other occurs. All right, two events are independent if the following are true. If the probability of A occurring, given that B occurred, is just the same as the probability of A, and the probability that B occurred, given that A occurred, is still just the probability of B. And here's a big formula for you to write down. The probability of A and B both occurring is the probability of A times the probability of B. This symbol right here, oops, that is not what I meant to write. This symbol right here, this is a math shorthand for writing and. And if we want to know the probability both A and B occurred, it's the same as the probability of A times the probability of B. So for example, the outcome of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability for the outcome of the second roll. If two events are not independent, we say they are dependent. Let's do an example of independent events. Let's roll a die 2 times, and here's my nice pretty sample space down here on the bottom right. Let event A be rolling a 1 on the first roll, and let event B be rolling a 2 on the second roll. What is the probability of rolling a 1 on the first roll and a 2 on the second roll? Well, there's only one way to do that, rolling a 1 on the first roll and a 2 on the second roll. So we could compute this by just actually counting up how many times that event occurred without using our formula. And we know that happens 1 time out of 36, right? By just looking at the sample space. Only one time can you get a 1 on the first roll and a 2 and a second roll when we say and in between them. I think that kind of looks like an and, so that helps me remember and. Let's use our formula that we just learned. The probability of A and B is equal to the probability of A times the probability of B. All right, let's find this, see if our formula works. Well, what's the probability of rolling a 1 on the first roll? Well, if you roll a die 1 time, what's the probability of rolling a 1? Well, that's 1 chance out of 6. Rolling a 2 on the second roll, well, there's one way to get a 2 out of 6 possible ways, so that is also 1 way out of 6, and we get 1 out of 36 using our formula. So we did it the first time, we just did it by looking at the sample space and actually computing the probability of A and B. The second time, we used our new handy-dandy formula to know that since the events are independent, we can multiply the probability of A by the probability of B to find the probability of A and B. All right, let's talk about dependent events. When we talk about dependent events, we need to talk about conditional probability, because when they're dependent, the probability of A is conditional upon the probability of B or vice versa. We write probability of A given B like that. That means we want to know the probability of A given that B has occurred, okay? A conditional, that bar, reduces the size of the sample space, all right? Because instead of anything occurring, we know that B must have occurred, okay? And we calculate the probability of A from the reduced sample space of B. Let's look at an example. Nice, straightforward example. We have our 1 fair 6-sided die, and our sample space is 1, 2, 3, 4, 5, and 6. Let's let event A be that we rolled a 2 or a 3, and event B be that we rolled an even number, so a 2, 4, or a 6. If we want to calculate the probability of A given B, we are asking what is the probability that we got a 2 or a 3 given that we rolled an even number, all right? Well, to do this, we count the number of outcomes, 2 or 3, in the reduced sample space of our new sample space B. So since we knew B occurred, it has to be a 2, 4, 6. How many times is either a 2 or a 3 in there? Well, once. There's just the 2, right? 3 doesn't ever happen, and 2 happens 1 time. So we divide the total number of outcomes of A and B, 1, divided by the total number of outcomes of B, which is 3. This gets a little bit confusing, but the way I like to think of it is, let's say your friend rolled a dice and you can't see the results. And you say, what's the probability that I got a 2 or a 3? and they give you the information that it was an even number. You're like, oh, well, if I know it's an even number, the probability that I got a 2 or a 3 is going to be 1 chance out of 3, because there's only 3 even numbers, and I have one of them, so my probability is going to be 1 out of 3. That helps a little bit. All right, let's talk about this nice formula that we have for conditional probability. Okay, so this formula says the probability of A occurring given B occurred is equal to the probability of A and B both occurring divided by the probability of B occurring. All right, so let's think about this in conjunction with our first example. Our first example, the example we just did, the probability that A and B occurred. Well, in our example, A was equal to the event that you rolled a 2 or a 3, and B was equal to the events that you rolled an even number, so 2, 4, or 6. So the probability of A and B occurring, that's only going to happen with a 2, right? A and B, the only guy that's in both of those is 2, right? The intersection of those two is just 2. So the probability of getting a 2 is going to be 1 chance out of 6. What's the probability of B occurring? Well, if we look up at B, there's 3 outcomes in B, a 2, a 4, or 6, out of a total of 6 outcomes. So there's 3 chances out of 6 that B occurs. All right, well, we can divide fractions. We know that 1/6 divided by 3/6 is the same as 1/6 times 6/3. Dividing by a fraction is the same as multiplying by the reciprocal. And when we multiply those guys, the 6's cancel out, and we get 1/3, just like we got the other way when we were thinking about it in a more theoretical approach. We can get the same answer by applying our formula. And sometimes the formula is just a little bit easier to use. All right, let's go over an example of dependent events. Let's roll a die 2 times, and which you may say is an independent event, but it isn't in this situation because my event A is that we roll a 1 on the first roll, but my event B is that the sum of the dice is 7. So if I roll a 1 on the first roll, that's going to change the chance of me getting a 7 on the second roll, right? Does that make sense to everyone? So those probabilities are dependent, because if I got a 1 on the first roll, it changes how many ways I can add up to 7. All right, so let's see if we can compute the probability of rolling a 1 on the first roll given that the sum of the dice is 7. So it's as if a friend is rolling the dice in a box and they're like, oh, it turns out to be a 7 for the sum. And you're like, oh, what was the probability they got a 1? The first roll was a 1. Okay, that's kind of the situation. So let's go ahead and see if we can figure this out using our formula. Our formula says the probability of A given B equals the probability of A and B divided by the probability of B. All right? Well, the probability of, let's start with the denominator, why not? The probability of B is the probability that the sum of the dice is 7. The sum of the 2 dice is 7. Looking at our sample space, we can see that 1 plus 6 is 7, 5 plus 2 is 7, 4 and 3 is 7, 4 and 3, 5 and 2 is 6 and 1. And I don't think anybody else is going to add up to 7. So of these 36 possible outcomes, 6 of them are 7s. 6 of them sum to 7, I should say. Of course, you can't roll a 7. All right, so that's the denominator, 6 chances out of 36. What's the numerator? Well, we want the probability that there was a 1 on the first roll and the sum of the dice was 7. So of our 6 choices were 7, there's only one that has a 1 on the first roll. So out of all 36 choices, there's only one of them that has a 1 on the first roll and a sum of 7. So the probability of getting a 1 on the first roll, given that the sum of the dice is 7, is equal to 1 over 36 over 6 over 36. Again, we all know how to divide fractions. 1 over 36 times 36 over, oh, that's dyslexia showing its face. 36 over 6 equals, dividing by 6, 36 is the same as multiplying by 36, 6. These guys cancel when I multiply my fractions, and I get 1/6. All right, hopefully that was pretty straightforward. Let's try one more example. It's a little bit trickier. All right, let's try a little bit harder example about dependent events. First of all, first thing I'm going to do before I even jump into this example is I'm going to look at this formula up here, and I'm going to notice that I can rearrange it just a little bit, and it's going to be very useful to rearrange this formula. One thing I'm going to do is I'm going to multiply both sides by the probability of B, and that gives me that the probability on the right-hand side, these guys cancel, of A intersect B equals the probability of A given B times the probability of B. This is a very useful formula. Okay, I put a box around this. And of course, the A's and B's are arbitrary, so it could be the probability of B given A times the probability of A. That would work out. All right, let's read the question now that we've done a little bit of pre-work. Riley buys a bag of cookies that contains 6 chocolate chip cookies. We'll call those guys C. 8 peanut butter cookies. We'll call those guys P. 4 sugar cookies, S. And 7 oatmeal, which we'll call O with a little swoopy on it. All right, what is the probability that Riley reaches into the bag and randomly selects an oatmeal cookie from the bag, eats it, then reaches back into the bag and randomly selects a peanut butter cookie? So what we want to know, the event we're interested in here, is that he gets a oatmeal cookie on the first draw, and then peanut butter cookie on the second. And that's an and statement. We want oatmeal on the first and peanut butter on the second. All right. I'm going to label my events in what may seem like the opposite order, but I think you'll see in a minute why I did that. All right. I'm going to define my events in maybe a little bit backwards way, but you'll see why in just a second. I'm going to let A be the event that peanut butter is the second cookie. And I'm going to let B be the event that O is the first cookie. And what I'm interested in is the probability of A and B. These are commutative. It's the event that peanut butter was the second cookie and oatmeal was the first cookie. Now I can use my formula up here, and it says the probability of A intersect B here on the right-hand side equals the probability of A given B times the probability of B. I'm going to start this formula by first figuring out the second part and then figuring out the first part. So what is the probability of B? What is the probability that oatmeal was the first cookie? Well, that one's not too bad. Let's see, how many cookies does he have in his bag? He has 6 and 8 is 14, plus 4 is 18, plus 7 is 25 total cookies. And we know that 7 of them are oatmeal, so the probability of B is 7 chances out of 25. All right? Now, what's the probability of peanut butter being the second cookie, given that oatmeal was the first cookie? Well, we know he has 1 less cookie because he ate 1, right? And the one he ate was oatmeal. So that means he still has 8 peanut butter cookies. So the probability in my bag of 24 cookies, 8 of them are peanut butter, the probability of getting a peanut butter one, given that he's already eaten an oatmeal one, is 8 chances out of 24. So that tells me that my entire probability of A and B, oatmeal followed by peanut butter, is equal to 8 over 24 times 7 over 25, which is equal to 56 over something. I need to calculate it for that one. 24 times 25 is 600. I don't know why that line keeps happening. And maybe we write this as a decimal. 56 divided by 600 is about 0.0933 if we go to 4 decimal places. This brings up a little bit of an issue in this last example, which I haven't talked about yet, but I'm going to talk about now, and that's with replacement and without replacement. When Riley ate that cookie, he didn't put it back into the bag, right? That's what we call without replacement. So with replacement means you draw something out, you look at it, write it down, and you put it back in. And those events are always independent because you go back to the exact same experiment each time. It's set up again to repeat exactly the same as before. No changes have occurred. Without replacement is like Riley eating the cookie. The next time he does experiment of drawing a cookie out of the bag, the probabilities are different because he has less cookies in the bag. Let's look at an example. If we were picking with replacement, we could draw some cards out of a standard deck. We pull a queen of spades out from 52 cards, we put it back. Draw another card, maybe it's a 10 of clubs. We're still drawing from 52 cards, we put it back. Again, we could draw the queen of spades again because it went back each time. If you're doing without replacement, you're going to be changing each time. Let's say you draw the king of hearts from 52 cards. You set it off to the side. Now you only have 51 cards to draw from. You draw the three of diamonds. Now you only have 50 cards to draw from. And each time the probabilities in the deck have changed because you're not having the same number of cards. All right, let's talk about mutually exclusive events. Suppose we have the sample space 1 through 10. A is the events 1 through 5. B is the event you get something 4 through 8. And C is you get 7 or 9. A and B is equal to the numbers 4 and 5. And the probability of A and B occurring could happen with probability 2/10 and not equal to 0. They're not mutually exclusive. How about A and C do not have any numbers in common? The probability that A and C both occur is 0. They are mutually exclusive. If you do not know if events are mutually exclusive, assume that they are not until you know for sure that they are.